Hello everyone, welcome to my channel Twinkle Teaches, and here is your friend Twinkle. Hope you all are doing good at your studies. In this video, we will discuss types of topological spaces. In my previous video, I have explained what is topology, why to study topology, and use of topology. You can find its link in the description box. But before we start, let's get a quick review to the definition of topology. A collection of subsets of X, that is tau, is called a topology on X if it follows three basic properties. First property says that the empty set and the set itself should belong to tau. The next property says that tau is closed under finite intersection. That is, if we collect finite number of members from tau and take intersection of them, then that will also belongs to tau. Third property says that tau is closed under arbitrary union. That is, if we collect any number of members from tau, then their union should also belongs to tau. If tau verifies these three basic properties, then we say that tau is a topology on X, and the pair X tau together is known as topological spaces. So this is about what is topology. Now let's come to the lesson, types of topological spaces. Can you guess any such type of topological space? Let's see. Discrete topological space. It contains pair X in power set of X, like X is a non-empty set and Px is a power set of X, that is a set which contains all subsets of X. This is known as discrete topology. Let's see if tau verifies all three properties of topology or not. First property says that X and phi should belongs to tau. Here, power set is containing elements like phi, G1, G2 and X. So here we can see that phi and X both belonging to the power set of X, and that is tau. So we can say that first property is verified. Come to the next property, which says that finite intersection of members of tau belongs to tau. Since if we collect members from power set of X belonging to it, then we find that their intersection will again be contained in that set, because X is the supreme set which is contained in that, and the smallest set phi is also contained in that. Come to the third property. Arbitrary union of all sets, or you can say of infinite number of sets, belongs to tau. So here let's see, does it verifies or not? X is the supreme set which belongs to power set of X. And if we take union of all subsets of X, it will again give us X, which is belonging to the power set of X. So the third property is also verified. So we can say that X in power set of X together forms a discrete topological space. Let's come to the next topic, indiscrete topological space. X is a non-empty set and phi is an empty set. Together they form a topology known as indiscrete topological space. Here, first property is clearly verified that X and phi both belongs to tau. The next property says that intersection of finite number of members of tau belongs to tau. Here are only two members. Phi intersection X gives phi, which is belonging to tau. So the second property is verified. Third property says that phi union X, which is equals to X, that is belonging to tau. So the third property is also verified. So we can say that this tau with the two elements verifies all the properties of topology. So it forms a topological space known as indiscrete topological space. Let's come to the next, co-finite topological space. Let X be a set, then co-finite topology on the set X contains a members like A such that A is a subset of X and either A is empty or the complement of A is finite. That is, A must be empty or complement of A must be finite. And what does it mean by finite? Either A is phi or A is equivalent to some subset of natural numbers. So this is about co-finite topology. So eventually what we get, the set X together with the co-finite topology is known as co-finite topological space, which is also known as finite complement topology. And here I am not going to follow the process to verify all basic three properties. You can check it on your own as an exercise. So let's come to the next, co-countable topological space. Let X be a set and the topology on X, which contains elements like A is a subset of X such that either A is empty or complement of A is countable. That is, either A is empty or its complement is countable. Such type of elements are only contained in co-countable topology. And let me tell you, what does it mean by countable? Countable means either finite or co-countable and finite. And finite means either A is empty or A is equivalent to subset of natural numbers. And co-countable infinite means A is equivalent to n or there exists a bijection from the set to the set of natural numbers. So it is about the co-countable topology. It is also known as co-countable complement topology, and the set together with the topology is known as co-countable topological space. Let's come to the next, nested topological space. and tau is containing elements like U1, U2, U3, where all these U's are the subsets of X and they are related with the nested property which says that phi is contained in U1 and U1 is contained in U2 up to UN minus 1 is contained in UN. So this property is known as nested property and topology comprising this property is known as nested topology on the set. Also, the set with this topology is known as nested topological space. Here are few frequently used topological spaces. Those are K topological space, lower limit topological space, and usual topological space. I'm not going to discuss the properties of these because they need the notion metric spaces, which I'm not going to discuss here. So hope you all have got these topological spaces which we have discussed here. Give your suggestions in the comment section, and if you need the PDF version of the notes I have used in this video, you can provide your email ID in the comment section and I will have you all these. Please don't forget to like, subscribe and share my videos. Enjoy learning. Thank you.